Physical properties of materials and systems are often described as intensive and extensive properties. This classification relates to the dependency of the properties upon the size or extent of the system or object in question. The distinction is based on the concept that smaller, non-interacting identical subdivisions of the system may be identified so that the property of interest does or does not change when the system is divided or combined. An intensive property is a bulk property, meaning that it is a physical property of a system that does not depend on the system size or the amount of material in the system. Examples of intensive properties include temperature, refractive index, density, and hardness of an object. No matter how small a diamond is cut, it maintains its intrinsic hardness. By contrast, an extensive property is one that is additive for independent, non-interacting subsystems. The property is proportional to the amount of material in the system. For example, both the mass and the volume of a diamond are directly proportional to the amount that is left after cutting it from the raw mineral. Mass and volume are extensive properties, but hardness is intensive. The ratio of two extensive properties is scale invariant, and is therefore an intensive property. For example, when gravity effects can be neglected, the ratio of the extensive properties mass and volume, the density, is an intensive property. This terminology of intensive and extensive properties was introduced by Richard C. Tolman in 1917. Intensive properties. An intensive property is a physical quantity whose value does not depend on the amount of the substance for which it is measured. For example, the temperature of a system in thermal equilibrium is the same as the temperature of any part of it. If the system is divided, the temperature of each subsystem is identical. The same applies to the density of a homogeneous system. If the system is divided in half, the mass and the volume change in the identical ratio and the density remains unchanged. Additionally, the boiling point of a substance is another example of an intensive property. For example, the boiling point for water is 100 degrees Celsius at a pressure of 1 atmosphere, a fact which remains true regardless of quantity. According to the state postulate, for a sufficiently simple thermodynamic system, only two independent intensive variables are needed to fully specify the entire state of a system. Other intensive properties can be derived from the two known values. Some intensive properties, such as viscosity, are empirical macroscopic quantities and are not relevant to extremely small systems. Combined intensive properties. There are four properties in any thermodynamic system, two are intensive and two are extensive. If the set of parameters are intensive properties and another set are extensive properties, then the function is an intensive property if for all. It follows, for example, that the ratio of two extensive properties is an intensive property. Density is equal to mass divided by volume. Examples of intensive properties include extensive properties. An extensive property is defined by the IUPAC Green Book as a physical quantity which is the sum of the properties of separate non-interacting subsystems that compose the entire system. The value of such an additive property is proportional to the size of the system it describes, or to the quantity of matter in the system. Taking on the example of melting ice, the amount of heat required to melt ice is an extensive property. The amount of heat required to melt one ice cube would be much less than the amount of heat required to melt an iceberg, so it is dependent on the quantity. Extensive properties are the counterparts of intensive properties, which are intrinsic to a particular subsystem. Dividing one type of extensive property by a different type of extensive property will in general give an intensive value. For example, mass divided by volume gives density. Combined extensive properties, if a set of parameters are intensive properties and another set are extensive properties, then the function is an extensive property if for all. Thus, extensive properties are homogeneous functions with respect to. It follows from Euler's homogeneous function theorem that where the partial derivative is taken with all parameters constant except. The converse is also true, any function which obeys the above relationship will be extensive. Examples of extensive properties include related extensive and intensive properties. Although not true for all physical properties, Some properties have corresponding extensive and intensive analogues, many of which are thermodynamic properties. Examples of such extensive thermodynamic properties, that are dependent on the size of the thermodynamic system in question, include volume, internal energy, enthalpy, entropy, Gibbs free energy, Helmholtz free energy, and heat capacity. The symbols of these extensive thermodynamic properties shown here are capital letters. For homogeneous substances, these extensive thermodynamic properties each have corresponding intensive thermodynamic properties, which are expressed on a per mass or volume basis. The name is usually prefixed with the adjective specific to indicate that they are bulk properties, valid at any location in a thermodynamic system. They may be dependent on other conditions at any point, such as temperature, pressure, and material composition, but are not considered dependent on the size of a thermodynamic system or on the amount of material in the system. Specific volume is volume per mass, the reciprocal of density, which equals mass per volume. L equals liter, J equals joule. Specific properties, expressed on a per mass basis, specific volume is the reciprocal of density. If a molecular weight can be assigned for the substance, or the amount of substance can be determined, then each of these thermodynamic properties may be expressed on a molar basis, and their name may be qualified with the adjective molar, yielding terms such as molar volume, molar internal energy, molar enthalpy, molar entropy. Standards for the symbols of molar quantities do not exist. A well-known molar volume is that of an ideal gas at standard conditions for temperature and pressure, with the value 22.41 liters per mole. Molar Gibbs free energy is commonly referred to as chemical potential, symbolized by I1/4, particularly when discussing a partial molar Gibbs free energy I1/4 for a component I in a mixture. Generality of classification. The general validity of the division of physical properties into extensive and intensive kinds has been addressed in the course of science. Reed-Leach noted that physical properties and especially thermodynamic properties are most conveniently defined as either intensive or extensive. However, these two categories are not all-inclusive and some well-defined physical properties conform to neither definition. Reed-Leach also provides examples of mathematical functions that alter the strict additivity relationship for extensive system, such as the square or square root of volume, which occur in some contexts, albeit rarely used. Other systems, for which the standard definitions do not provide a simple answer, are systems in which the subsystems interact when combined. Reed-Leach pointed out that the assignment of some properties as intensive or extensive may depend on the way in which subsystems are arranged. For example, if two identical galvanic cells are connected in parallel, the voltage of the system is equal to the voltage of each cell, while the electric charge transferred is extensive. However, if the same cells are connected in series, the charge becomes intensive and the voltage extensive. The IUPAC definitions do not consider such cases. References: Corlin, Herbert B. Thermodynamics and an Introduction to Thermostatistics. New York, John Wiley & Sons. ISBN A0-471-86256-8. Lewis, G.N. Randall, M. Thermodynamics. New York, McGraw-Hill Book Company. Linda, Bruno. Thermodynamics and Introductory Statistical Mechanics. New York, John Wiley & Sons. ISBN A0-471-47459-2A.